So our next speaker is Chris Fuchs. He's a professor of physics at the University of Massachusetts in Boston, a world-renowned quantum physicist, and a fellow of the American Physical Society. He held the Lee Dubridge Prize postdoctoral fellowship at Caltech and worked for many years at the Perimeter Institute at Waterloo, Canada, which is actually where we met, I think, originally.
I invited you to a conference.
That's right. He's the author or co-author of more than 100 scholarly pieces, has one article that has 13,000 citations.
No.
Okay, sorry. That was somebody else.
I would like that.
I just heard something about a guy has, was Steve Strogatz, has an article that has 30,000 on fireflies and synchronization.
It's funny, I do mention in this talk an article that has 13,000.
Oh, that must be it.
But it's not mine.
Oh, okay. That must be why I got confused. Okay. Yeah, I guess I should work in fireflies. So a collection of his email exchanges with peers on foundational issues of quantum mechanics was published by Cambridge University Press as Coming of Age with Quantum Information. And another much larger collection was posted as the 2,349-page document, My Struggles with the Block Universe. So there you go, Janan. It's a complicated issue, this block, and the lovers of becoming. Fuchs credits John Wheeler's thinking as a central influence on his views on quantum mechanics since early in his career. And for that, he must be commended. Thank you, Chris.
Thank you, Marcelo. I was at a meeting in Paris maybe 4 weeks ago, with Michel Bitball. And there I gave a talk titled The Day Cubism Shot Itself in the Foot. And I liked my opening slide so much, I thought maybe I would use it again here because of a meaning that will become clear. But the thought just struck me that Marcelo is such a good chairman. I had better be careful not to shoot myself in the foot by going overtime. I guess I would say that my philosophical awakening occurred in 1999. I was presenting a theorem in quantum information theory at the Newton Institute in Cambridge, and it was a theorem about how to understand interchanging quantum systems and what kinds of quantum states resulted because of that. And at the end of my talk, someone in the far back of the audience boomed out in a very thick Scottish accent that I was nothing but an American pragmatist. And I didn't know about William James at the time. I didn't know about Charles Peirce. And I didn't know what it meant to be an American pragmatist. I tried to capture the guy and corner him at the end of the talk, but I couldn't get to him. And this sort of nagged at me for a few months until I came across an essay by Martin Gardner titled Why I Am Not a Pragmatist. I read the essay, and as I was reading it, I had this rather funny reaction that every time he would give an example of how a realist would speak versus how James or Dewey would speak, he would say, well, you can speak the way that they do, but it's just an encumbrance. It doesn't clarify anything. Better to just speak in the old realist fashion. And for each of these examples, I would think to myself, no, that's not right. If you're thinking about measuring, for instance, a spin, rather than turning over a card and looking at the suit that's underneath it, then actually it's not an encumbrance to speak in these ways. It's the more natural way to speak. So by the end of the article, I had appreciated I am an American pragmatist. And that has shaped my thinking since. Now, lately, by hanging out with Michel Bitball and some of his colleagues, they're trying to convince me that I'm not only an American pragmatist, but I'm a phenomenologist, and that Merleau-Ponty would not disapprove of what I'm saying. The way I've viewed cubism, or my foundational approach since 1999, actually has been in the following way, that by using the mathematics of quantum theory, whatever that is, you don't have to be an expert, and you don't really have to care what that symbol means, but we use symbols like that all the time. And the idea struck me that by using the precise structure of quantum theory as a kind of workshop, a philosophical workshop, perhaps we can make some of the issues that I actually was so attracted to in William James's writings, we could make it much more clear and make it much more convincing and make it seem like something more than just an arbitrary philosophical choice. So I thought perhaps I would give you some sense of the history of how this has gone and how it has led me to the day in about 2008 when, according to a colleague, I finally shot myself in the foot. Shooting myself in the foot, in fact, is the reason I'm at this conference, because it was the first time that I had appreciated with full clarity that the way I was thinking about quantum measurement was purely in terms of experience, not in terms of classical amplification or some other terms like that. So cubism essentially started with a demand by Edwin James, who said, "Our present quantum mechanical formalism is a peculiar mixture describing in part realities of nature, in part incomplete human information about nature, all scrambled up by Heisenberg and Bohr into an omelet that nobody has seen how to unscramble. Yet we think that the unscrambling is a prerequisite for any further advance in basic physical theory, for if we cannot separate the subjective and objective aspects of the formalism, we cannot know what we are talking about. It is just that simple." Carlton Caves, my PhD advisor, pushed this idea upon me. And particularly, he pushed the idea that the reason we want to unscramble the omelet is that perhaps this will give us explanatory power for a range of phenomena that other interpretations just didn't have. With an interpretation like the Bohmian interpretation, they might say, well, we can understand quantum teleportation too, after somebody shows us the phenomena. We can explain it in hindsight. Caves was the first person who pushed upon me the idea that this immediate explanatory power can help us find new phenomena that we might not have found otherwise. And I think maybe one of the best examples of this is something in the literature known as quantum teleportation. That's the paper with nearly 13,000 citations. Well, in fact, it had 12,784 yesterday, and I think it has a few more today. So the phenomenon of quantum teleportation is something that was considered shocking at the time of its discovery. And let me just give you a feel for how the phenomena goes. It's a game that is taking place between, in quantum information, we always have someone named Alice. Let's see, does this work? Oh, well, anyway, there's Alice up there. There's Bob down here. Alice has in her possession a quantum system, say an electron, with some quantum state associated with it. And she's given the instructions to get a quantum system with that quantum state into the possession of Bob. Now, here's something to recognize about quantum states. A quantum state for an electron can be parameterized by two complex numbers. Complex numbers live in a continuum. So you might say that it takes an infinite amount of information to represent a quantum state. So Alice needs to get to that system that has a representation containing an infinite amount of information down to Bob. The trouble is, there's a wall between them, and she has no physical means for getting her an electron through the wall. So what can she do? Well, these six guys that I showed you in the photograph earlier came up with a rather novel idea. And it was this, that if Alice and Bob previously shared two other quantum systems that we would describe as entangled, then there was something Alice could do on the two systems in her possession to transfer the quantum state across the wall down into Bob's possession. So the story was, Alice could perform a measurement. I really wish I had a pointer. I don't have a pointer, I guess. Unless, nope. Now I have a pointer. Oh, there it is. Yes. So Alice could perform a measurement on these two quantum systems. She could get on the telephone, speak to Bob. When Bob got the message, he could simply take his electron and turn it this way, or turn it that way, or turn it the third way, or do nothing at all. And the miracle of quantum teleportation is that the state ceased being up there and now appears down here. But she performed a measurement that has 4 outcomes, and only 4 outcomes. And she gets on the telephone, and she conveys to Bob 2 bits of information, in other words, which result of the 4 outcomes. And somehow, this state that's described by an infinite amount of information, the exact values of 2 real numbers, appears down there. Well, one of the founders, Richard Joseph, says teleportation appears paradoxical. Only 2 classical bits were sent, so how did the full quantum information pass from Alice to Bob? This leads to an intriguing interpretation. In addition to the 2 bits, the remaining quantum information must have been propagated backwards in time from Alice to the source of the 2 particles, and thence forward in time to Bob. Indeed, if we insist that information transmission requires a physical channel, then there appears to be no other possible interpretation of the teleportation process. But if we took this idea of Jane's rather seriously, that a quantum state is some scrambling up of objectivity and subjectivity, in fact, you could give a rather simple, and in fact, so simple of an explanation that if I had the time in this lecture, I could pull 3 coins out of my pocket and give you a kind of parlor game demonstration of exactly what quantum teleportation is without requiring a multi-million-dollar laboratory. The key to it is that this quantum state that Alice had shouldn't be thought of ontically. It shouldn't be thought of as a property of the system, but rather it arises because it's the state of knowledge of someone who's been left out of the diagram. Call him Charlie. Charlie has a certain amount of information or a compendium of beliefs about the system where I've drawn the psi. But what you should understand is that this is Charlie's information about this particle. And if it were really drawn properly, it should be up here in the cloud where Charlie's head is, because it's his information. When Alice performs the measurement and gets on the telephone and calls Bob, and presumably Charlie is listening in, all that is happening in the quantum teleportation process is that Charlie says, oh, the information that I had, which was relevant about this one, is no longer relevant to that one. It's relevant to this one. Nothing has traveled. The only thing that has traveled is Charlie's reference. It has traveled in the pointer of his mind from being information about this to being information about that. And that solves the paradox. And in fact, as I say, I can do a little parlor trick, or maybe tonight at dinner if any of you would like to see. If you'll bring me 3 coins, and I'll give them back, I can show you how to do it. When we first found maybe 15 examples like this, we thought this will really impress the philosophers. And they'll start thinking that quantum states are not ontic after all. They should be thought in epistemic terms. Well, it didn't much impress most any philosopher of science. A good example is Tim Maudlin, who really hangs on one certain phenomena in quantum information, or one certain phenomena in quantum physics. Tim says, what Bell proved, what John Bell proved, and what theoretical physics has not yet properly absorbed is that the physical world itself is non-local. What he means by that is what you do right here and now can affect things far away, all the way across the universe, 5 billion light years from here. You do it here, something instantaneously happens over there. Someone in the far universe sneezes, and it affects what's going on in the laboratory here. Well, physicists are generally suspicious of this idea. I think no one put it better than Einstein, who said he wouldn't know what physical science meant if we couldn't isolate the things in our laboratory so that our tests and our manipulations of them become meaningful. So thinking like this and wanting to make an airtight conception of quantum theory caused us, Bayesians, cubism, quantum Bayesianism, you mentioned it in your talk, that's an old name for it. We've outgrown that because there are too many varieties of Bayesians, as some of the philosophers in here know. There's 46,000 some odd varieties of Bayesianism, according to John Good. A better word comes from Oliver Wendell Holmes Jr., who invented the notion that he called betabilitarianism. He believed that the universe had a certain element of chance to it, but we can bet on this universe in its contact with us, an important piece of his thinking. So I now think of cubism as standing for quantum betabilitarianism, but I don't say that too much because it's a tough word. Well, this causes us to think much harder about what we do with quantum states. And inevitably, in quantum theory, you calculate probabilities from quantum states. But one of the things that we learned in quantum information theory is that, in fact, it can go the other way around. If you consider a robust enough set of quantum measurements, and the robust set is a finite set of quantum measurements, if you consider a certain finite set of measurements, then the probabilities uniquely specify quantum states. So this leaves open the idea that, in fact, a quantum state is nothing more than a set of probabilities. Or, in the extreme, if you do it just right, a quantum state is nothing more than a single probability distribution. So this causes us to think hard about, well, what are the probabilities in quantum theory? Indeed, what are probabilities at all? Going in that direction, we ended up landing on one of the extreme rare varieties of Bayesianism that is associated with Bruno De Finetti. If we want to get rid of tickle, 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 then probabilities, in fact, have to be banished from the world. De Finetti said, my thesis paradoxically, a little provocatively, but nonetheless genuinely, is simply this: probability does not exist. What he meant by that is that probability is not something manifest in the world without agents using the probabilities for making their decisions. He thought that a great clarification would come about by adopting that conception of probability, and in fact, we agree that it does. So consider a coin. There's some probability for it landing head, some probability for it landing tail. The subjectivist notion of probability that De Finetti developed would say that these are not things intrinsic to the coin. The probabilities are not intrinsic to the coin. The probabilities are not intrinsic to the mechanism of flipping the coin. In fact, there's nothing about the coin that can tell you what an agent believes of the coin. If I ask a coin about my expectations of it, it'll laugh. Don't ask me, I don't have a clue. That's your business, the coin says to me. Ask yourself. Maybe a little more informatively, here's something Dennis Lindley said. The topic studied is the situation of an individual. This is key and important. An individual who's faced with uncertainty about some events of concern to him. All of us find ourselves in this position. De Finetti's task is first to recognize openly the uncertainty surrounding us, and then to see how we can best understand it. If we live in a quantum world, we're certainly surrounded by uncertainty. If we live in any world, we're surrounded by uncertainty. If we take a walk across the street, we're gambling with our life, each and every time. So De Finetti's task is to first recognize openly that uncertainty surrounding us, and then see how we can best understand it. The main result is that uncertainty can only be described satisfactorily in terms of the calculus of probability. The Bayesian subjectivist or coherent paradigm, all equivalent names, is egocentric. It is a tale of a single person contemplating the world and not wanting to be stupid. He realizes that to do this, his statements of uncertainties must satisfy the laws of probability.
Can I ask a clarifying question?
Yeah, sure.
So
I love clarifying questions, but you be nice to me. This goes on the
this is real
clock.
quick. Is it also part of this view that the world is deterministic, or is that not necessarily part
That
of
is
it?
not necessarily part of it.
Okay.
This notion of probability could play out in a deterministic world, and it could play out in an indeterministic world. And I am one who is a strong believer in epistemic probability, so non-objective probabilities, but also in an indeterministic world. But by indeterministic, one means something different than David Lewis's chance, or propensity views of probability. So just to give you some sense of what it means to not be stupid, here's how it's formalized. When there is a bookie who has published odds that he's willing to accept, on, let's say, on a horse race, so he writes down the probability for E, probability in quotes, because this is the primitive notion. We don't know that it satisfies the calculus probabilities yet. Probability of not E, probability of E or F, probability of not F, so forth. When he writes down probabilities for events, all he means by this declaration is that he's willing to buy or sell a lottery ticket worth $1 if the event E occurs for this much money. Are those numbers right or wrong? There's no sense of that. It's just how the bookie is willing to set the gambles. The genius of Diffinetti was that he noticed that if you add one rule to that, never declare numbers that will lead to a sure loss. So if someone comes up to the window and says, here, I will sell you so many tickets, it's at your price. I will buy so many tickets for another event. I will sell you so many for this, for all of the various events that we had listed there. Diffinetti said the numbers had never be such that someone can come up and take the house. And from that, he was able to derive all of the standard rules of probability theory. Okay, that's what probability means in the subjectivist notion. It's just the numbers that one writes down, numbers for lottery, for how much they're willing to buy and sell lottery tickets for. Consider the extreme case under that conception. What means probability 1? It means one will buy or sell a lottery ticket worth $1 for, in fact, $1. Full stop. That's all it means. Probability 1 doesn't imply the truth of a proposition or the existence of something. It just means that someone is willing to take an extreme position based on, perhaps, their previous experience. Was Richard Jeffrey your advisor, Jeanine?
No, but he was one of my, he was there when I was.
Well, he's become one of my heroes.
Yeah, he.
Because he anticipated this idea far before us. The Bayesian framework replaces affirmation and denial by a continuum of judgmental probabilities in the interval 0, 1, endpoints included, or what comes to the same thing, a continuum of judgmental odds in the interval 0 to infinity, endpoints included. 0 and 1 are probabilities no less than 1/2 and 99 1/100ths are. Probability 1 doesn't imply the truth of a proposition. That's key to this notion of probability. And from that, we arrive at the first tenet of cubism. All probabilities, including all quantum probabilities, are so personal or subjective, they never tell nature what to do. This includes probability 1 assignments. Quantum states thus have no ontic hold on the world. So how is this relevant? Well, part of the foundational debate in quantum theory was set by Einstein, Podolsky, and Rosen in 1935, who said, if without in any way disturbing a system, one can gather information required to predict with certainty, i.e. with probability equal to unity, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. If I can make a measurement on 1/2 of an entangled pair of particles, and based on that make a probability 1 assumption, probability 1 prediction about something far away, Einstein, Podolsky, and Rosen said there must be an element of reality corresponding to the prediction I just made. Tim Maudlin says, with great clarity, if I could make one change to the EPR paper, in retrospect it would be to alter the characterization of this criterion. The authors call it reasonable and in agreement with classical as well as quantum mechanical ideas of reality, but its status is actually much stronger than that. The criterion is, in the parlance of philosophers, analytic. That is, this criterion follows just from the very meanings of the words used in it. Well, it's not so in cubism, because the meaning of the word probability in it is not the meaning of the word in Tim's analytic statement. Probability corresponds to gambling attitude, and probability 1 corresponds to gambling attitude. That at least gets rid of the necessity of the tickle, tickle, tickle. So cubism started from wanting to break the subjective and objective pieces of quantum theory apart, and then it encountered the question of locality and realized it had better take a radically subjective stance on probabilities. But does this carry a cost with it? And somewhere along the years, we started to realize that we have to ask this question. How much of the infrastructure around quantum states must be subjective as well in order to stave off inconsistency in this point of view? For instance, Niels Bohr would draw quantum measuring devices like this, these big, heavy objects bolted to tables. And the thing he wanted to emphasize is that the measuring devices, once the quantum systems have entered them, the measuring devices are as classical as anything we ever encountered in classical physics and carry an objective weight that quantum states, quantum systems don't. But if you think carefully about what measuring devices do to the incoming quantum systems and how they spit them out, then there are certain rules associated with that. We have a quantum state going in, quantum state going out is a quote-unquote collapsed quantum state, or something more generally that is specified by Luther's rule. And if you've taken the stance that there is no right and true quantum state already, then you have to take the stance that Niels Bohr's very solid measuring device is just as diaphanous as a quantum state assignment, and a quantum state assignment is just diaphanous as a probability assignment. So this is one thing that the infrastructure has to yield if you're going to take the radical stance on quantum states. Even quantum measuring devices are of the same character as a subjective probability assignment. You can go further. You can think about the Schrödinger equation. And it turns out, I won't give you any details, but you can apply nearly all of your favorite arguments for the subjectivity of quantum states to unitary time evolutions as well. And when I say nearly all, actually it is all, but you have to be a little more clever about it. Anything that you view as an argument for the subjectivity of quantum states, if you're consistent, you have to also accept it for unitary time evolution, consequently Hamiltonians in the Schrödinger equation. So this leads actually to a refinement of tenet 1.0. Tenet 1.1, all probabilities, including all quantum probabilities, are so personal or subjective, they never tell nature what to do. This includes probability 1 assignments. Quantum states, measurement operators, and unitary evolutions thus have no ontic hold on the world. So it looks like everything has gone up in a big deconstructive puff of smoke. But there is something that I would say in the formalism that does appear to have an ontic hold on the world. Something that is representative or reflective of some particular aspect of the world. And I would say that's not the quantum states or the measurement operators that go in, the quantum states are the measurement operators that go into this nice little compact way of saying, I calculate a probability from it. I would rather say, okay, that's subjective, and in fact, that is subjective on the left, P of I. But the way of combining these three different terms is an objective feature of quantum theory. But we shouldn't think of this objective feature in the sense of a law of nature as it's usually construed. Rather, it's something we should strive for. What do I mean by that? If we think about de Finetti's derivation of probability, what he was able to derive were the laws of probability theory. There's nothing that gives a derivation of the actual assignments of probabilities. But if you want to be safe from being taken to the cleaners, as I think it's called, then you had better make sure that all of your various probability assignments fit together according to the calculus. So it's the calculus that is an objective feature of probability theory, not the particular assignments. And similarly, I would say of this thing called the Born rule, if you do some decently advanced mathematics, you can finagle the Born rule into a statement that is purely about a prior probability assignment, some conditional probability assignments, and the assignment of a probability to measurement outcomes. The Born rule is some kind of addition to Dutch book coherence that, rather than being logical, as Dutch book coherence should be, I would say is empirical. The world could have been different. We could have run across a different theory for describing it, in which case we might add some extra normative rules for our probabilities, but it would not be this very simple one that quantum theory allows if you use the right formalism. So this gives us tenet 2. The Born rule, the foundation of what quantum theory means for cubism, is a normative statement. It's about decision-making behavior any individual should strive for. It's not a descriptive law of nature in the usual sense. It's not a descriptive law of nature in the sense that nature must obey it. Rather, it is that agents flowing in the stream of nature, making decisions, acting on nature, would, to their best interest, try to make sure that their probability assignments for various experiments fit together according to the Born rule. Okay, here we go. Thinking about all of this and taking this seriously, we also have to think about Wigner and his friend. The fellow on the left is Wigner, and sadly, maybe it depends upon which physicist you talk to, the friend on the right is Edward Teller, one of the fathers of the Cold War. So you might think that Teller is looking at Wigner here, but in fact, Teller is looking at the light switch, contemplating what might happen if he were to reach out with his hand and flip the switch. As far as Wigner is concerned, Teller is just a physical system behind him. He's not having a look at him. And as far as Teller is concerned, well, he's just interested in what that light switch will do. From Teller's point of view, when he flips the light switch, he will have an experience, he'll find a result. From Wigner's point of view, well, he can't see Teller, so he might, if he wanted to, make the best decisions, use the quantum mechanical formalism to check whether he was coherent with respect to it, and therefore he might use a unitary time evolution to describe the whole process of everything that's going on in the back. Well, that basically leaves you in the conundrum. Do you think of quantum measurement outcomes, as Bohr did, as objective states of affairs? Or should you recognize that perhaps we need a relativized notion of outcomes, in fact, thinking of them in terms of experience? Here's something I wrote in a 2010 paper. Whose beliefs? Mine. Beliefs about what? In those days, I used the word information, so I did cheat here. I modernized it a bit. I took beliefs. The consequences for me of my actions upon the physical world. The answer to the first question surely comes as no surprise by now, but why on earth the answer to the second? It's like watching a quantum Bayesian shoot himself in the foot, a friend once said. Why something so egocentric, anthropocentric, psychology lady, myopic, positivistic as the consequences for me of my actions upon the system? Why not simply say something neutral like the outcomes of measurement? It is, in fact, purely and only to keep Wigner and his friends' views both valid. So this leads us to tenet 3 of cubism, and I'm probably nearing the end of my time. A quantum measurement is any action an agent takes upon the world, and its outcome just is the consequent personal experience this induces in the agent. Particularly, quantum measurement outcomes are not, to paraphrase Bohr, instances of irreversible amplification objectively recorded for everyone to see, and advice whose design is communicable in common language suitably refined by the terminology of classical physics. I once found a sentence by Niels Bohr with over 200 words. And I'm not exaggerating. So here's the whole picture of cubism. Some of you have seen it before, but here's the way we think of quantum, basically what quantum theory is about. When we talk of quantum measurement, we conceptually split the world into 2 pieces. There is an active agent and the external world. Say a little quantum system here drawn as a cube for cubism. So the quantum system is a little cube here. The agent can take an action on the system. That's what we used to call quantum measurement. Taking an action on the system leads to a consequence for that agent, an experience. I draw the quantum state up here next to the head of the agent because I want to make it clear that the quantum state is not attached to the object here, but really it's his expectations for what experience he will receive upon taking an action on a system. It should really be realized how cubism differs from, I believe, all other interpretations of quantum theory. Imagine, if you will, that I take an eraser and I start erasing the agent out of the picture. So I just erase it conceptually, and there's the quantum state that was up near his head. What happens if we wipe the agent out of the picture? Well, then the quantum state goes poof. It's gone. Quantum states are not out in the world. And say, under the presumption that we are the only calculating agents that have achieved the stage that we did as of 1925, 1926, then quantum states appeared in the world in the heads of the agents who were using them. But there were no quantum states in the world before there were practitioners of quantum theory. So the quantum state went poof because I conceptually wiped out the agent. But the external world didn't go poof. So I would draw a distinction between cubism and solipsism. There is always the presumption of an external world from the very beginning. Quantum formalism tells us something else doesn't go poof. I believe quantum formalism tells us this. Namely, the normative relation that we should use should there be an agent in the story. The normative relation is still around for anyone to use who might discover quantum mechanics. It's telling us something about the character of the world, or at least something that we hypothesize about the world, given what we have experienced of it. I have 2 more minutes left, I think. Good. So I want to now just go to the point of this meeting, and I wasn't able to tell you or express as much as I would have liked to have. But I'd like to explore just very briefly what else might the tale of cubism be telling us about the stuff of the world, given its point of view on measurement. And actually, I'm very fortunate to have Amanda Gefter in the audience. I didn't know that she was going to be here. She gave us a talk in South Africa last summer, and I was so taken with it that effectively I've stolen her slides, and she's been kind enough to let me use them. She made a play on John Wheeler's famous U with the eye looking back at the beginning of the universe, and put it this way: there is maybe one little piece of a forest, I'm not sure how she thought of it, and there's our agent, and she has a little circle drawn down here with the symbol H for Planck's constant on it. I think she captures to the T what I'm aiming for in the next stages of cubism, and the reason Michelle Nell tells me that I'm a phenomenologist and I didn't know it. And so I'm just going to read Amanda's words, her own words, they're not mine. So she draws this picture and she says, you have a subject and an object, and mostly they seem like separate things, but when you look closely enough, you find that they are conjoined, that there's this piece of connective tissue where they can't be pulled apart, because within that region, there's no way to say which is which. The discreteness that we find in quantum mechanics is not a property of the object. It's a property of the subject-object relation. I think a useful way of thinking about this is to see Bohr's quantum of action as a kind of coupling constant between subject and object, between observer and observed. As you turn the strength of that coupling down, the area of overlap gets smaller and smaller, and if you turn it all the way down to zero, observer and observed can be neatly separated. It recovers classical physics and it frees the object from its subject so that it can be shared by other subjects. When h equals 0, there you go. Everybody is now decoupled from the stuff that is out there. But of course, h is not 0, and so we have to contend with the irreducible coupling between subject and object that Bohr would say is the very essence of quantum physics, and I would say ought to inform our philosophical discussions, in that realism is about an object decoupled from any subject, which you can't do, and idealism is about a subject decoupled from any object, which you also can't do. But what does that leave you? Well, Wheeler put it this way. It's difficult to escape asking a challenging question. Is the entirety of existence, rather than being built on particles or fields of force or multidimensional geometry, built upon billions of elementary quantum phenomena, those elementary acts of observer participancy, the little connective tissue, those most ethereal of all entities that have been forced upon us by the progress of science? There was a theologian in the audience who said, Dr. Wheeler, who was there to observe the universe when it started? Were we there? Or does it only start with our observation? Is the Big Bang here? Wheeler said, a lovely way to put it. Is the Big Bang here? I can imagine that we will someday have to answer your question with a yes. So I leave you with this thought, that perhaps the fundamental spark that we call quantum measurement, this stuff that's neither subject nor object, is the stuff of the world that really makes it fly. And the next stage of physics, I think, is developing this idea in the context of some of the mathematics that Cubism has brought us to. Thank you.